Hi, everyone. Thank you for joining us today for our webinar on uncovering molecular details through vibrational some-frequency spectroscopy. Beth, can you advance the slide, 2 slides? One more. All right. So our next webinar is going to be on June 11th, and that one is going to focus on high-res imaging capabilities for critical minerals research. More information will be provided over our social media channels and via email, so be on the lookout for that information and all of our upcoming events and other opportunities. Make sure that you're getting all of our information by subscribing to our email list if you aren't already a subscriber, and our multiple social media channels and platforms. And the links will be provided in the chat for you. For today, Beth, if you can advance the slide one more. Today's presenter is PNNL chemist Zheming Wang, who is going to discuss the principles behind some frequency generation spectroscopy and its applications in furthering energy and environmental research. And he's also going to showcase how it was used in some recent EMSL user projects. There will be time at the end of today's webinar for questions, and we encourage you to post your questions in the Zoom chat so that Zheming can answer them after he's done presenting. And so with that, I'm going to turn it over to Zheming. Thank you.
Okay, thank you for the nice introduction. Is the control on my side yet? Not yet. Okay, good. I think it works now. Okay, here's my title. Uncovering molecular details through vibrational some-frequency spectroscopy. Okay, we know that interfacial reactions dominate in most chemical processes in nature and also in many chemical processes in the engineered world. I give a few examples here, from the top right, where we have the electrode for electrolysis of battery operations, to ion exchange and solvent extraction, to a lot of the nucleation and precipitation processes, as well as like in nature, like those iron cycling process by microorganisms. And also, for a lot of critical elements, they are adsorbed at clays and, phyllosilicate minerals at the interlayers, where the reactions and the adsorption also occur at the interface. Of course, for any heterogeneous catalysis reactions, and the reactions for sure occurring at the interface. And same as all the things going on in the gigantic oceans there, all the soils and sediments, they will dissolve and they will nucleate, they precipitate, form new minerals. And of course, the atmosphere interact with ocean surface and carbon dioxide got exchanged and absorbed. However, as we can imagine that chemical reactions that are happening at the interface, the molecules involved are only a tiny fraction of the entire mass. And because of that, the most techniques when we use to analyze these chemical systems, the signal that are displayed by the interfacial chemical reactions and species are suppressed and overwhelmed by the bulk signal. So we really need techniques that can selectively monitor and probe the surface reactions. There are a few techniques at our disposal at the time being. We have those techniques such as grazing angle X-ray scattering, grazing angle neutron scattering. The accurate scattering will handle heavier elements, and neutron scattering and handle the lighter element. And of course, we have high resolution atomic force microscopes that can see the topography with atomic resolution. However, these techniques, while they give the topography and atomic coordinates of the atoms, but they don't really give, any chemical interaction or bonding information. That's where the some frequency generation and second harmonic generation, which is a special case of some frequency generation, come into play. These techniques can actually give exact the bound vibrations, how chemicals interact, and from this information we can get a lot of characteristics and parameters about these reactions and chemicals. Okay, a little bit of history. The phenomena of second harmonic generation and some frequency generation was observed in the early 1960s, right after the invention of laser. In 1960, the ruby laser was invented, and right after that, in 1961, a group of researchers at University of Michigan, in the Randall laboratory, they shine ruby laser through a quartz crystal, and then after passing through a spectrograph, they detect what's the light being passing through. And what they saw that was, beside that laser of ruby, that is 694 nanometer, they also saw there is a line at 347 nanometer, which exacts the second harmonic there. That was the first observation of second harmonic generation. And shortly after that, in 1962, by that time, there has been already a report that ruby laser, if you operate at room temperature and operate at the liquid nitrogen temperature, the laser emission wavelengths actually differ by 10 angstroms. So from that, the same research group, they operate one laser at room temperature, another at liquid nitrogen temperature. Then they collinearly pass both lasers through a glycerin sulfate crystal, and they detect on the photographic paper, they found that there are 3 lines beyond around the 347 region, beyond the 2 second harmonic of the room temperature laser and the liquid nitrogen temperature laser line. There is also a line right in the middle. So then they observed that actually beyond second harmonic, there can also be a sound frequency generation. That's really excited a lot of people. And actually, right after the second harmonic generation observation, Professor Bloomberg's group at Harvard University started deriving those mathematical equations. And during the process, they realized that these optical processes actually have some special properties at the boundaries of phases. And it is potential for these techniques to be used to selectively detect molecules at interfaces. That's from there, several graduate students, many people in the field would know that Professor Yuanyang Shen at University of California at Berkeley, and several other people start trying to see if these things can be actually put into application for chemical studies. And indeed, in 1981, in Professor Shen's group, they were able to use a second harmonic generation to study gas adsorbed on silver surface. And in 1987, he actually put some frequency vibration of some frequency generation into operation to study chemical reactions at both air-liquid interface and liquid-solid interface. So in a nutshell, some frequency generation, some frequency generation basically means that you have two laser beam, they just add together. In second harmonic generation, it's the same laser beam that add twice, become a new frequency. In the case of some frequency generation, like in this case, you have an infrared beam and a visible beam. You add together collinear and you incident on the same spot. You end up generating a beam that with the energy equals the sum of these two. Okay, the beauty, and that was just exemplified by the derivation of the mathematical derivations that because these are second order optical processes, they can only become non-zero when the media has no central symmetry. Any place, if the molecule has a central symmetry, there is no signal. So for most bulk solid and bulk solution, there is always one way or other that you have a central symmetry, so there is no signal. But at interface, no matter it's air liquid, air solid, or solid interface, where you have a change of the phase, the molecules by themselves are no longer central symmetric, then they have a signal. So that's the beauty of this technique. It is an intrinsically interface selective laser spectroscopy technique. Oh, actually, before I go too far, I just want to mention that the other thing I should mention that, this is a general principle here. However, it was observed and also derived that if any of these frequencies happen to overlap with a band of absorption band of a molecule, no matter it's an electronic transition or vibronic transition, that signal of some frequency generation can be greatly amplified. So because of that, we can actually probe the vibrational spectra of molecules, just like infrared and Raman. Okay. And as what I said, as long as there is interface and we can detect. So this technique can be applied to many chemical reactions, from solid liquid, ionic solutions, the surface of air with concentrated electrolytes. And of course, for ions that sorbed on surface, organic sorbed on surface, and so on and so on. I'm not going to spend time to just point them out. I have a list here, and we can, if you're interested, you can just look at. Okay, and thanks to BER office, and also thanks to EMSL, and also the Dr. Zheming Wang and his postdocs, Joe Lu and Luis Valadi. EMSL in the environmental spectroscopy laboratory, we are fortunate to be able to set up two systems 10 years ago. These systems are still operating, and particularly the picosecond scanning VSFT system. It's basically a workhorse, almost working every day and cracking out data to support our research. And this system is an X-Plus system. Basically, it's a neodymium laser-based system. We double the light to 532. And then we mix 532 and the fundamental frequency at 1064 generate 355 nanometer. And then using a differential frequency generation system, we generate the mid-infrared. And then we mix the mid-infrared light and the remaining 532 light and generate the some frequency. And like most of the vibrational some frequency generation spectrometers, we keep the 532 nanometer constant, and then we scan the vibrational frequency of the mid-infrared from about 1,000 wave number to 4,000 wave number, and then look at the vibrational spectra. So in a sense, it's basically just like Raman and infrared. You are recording the mid-infrared vibrational spectra. However, in this case, we are selectively detecting the interfacial molecules. And of course, we have a whole suite of, resource and other attachment here, such as osmosis angle scanning system, automatic polarization control, gas flow, liquid flow cell, and temperature control. So that allow us to handle a lot of chemical system that need to be probed. We also have a second system, it's called broadband system. In this case, we use a synchronized picosecond pulsar laser and a femtosecond pulsar laser. And because of that, we were able to achieve the resolution of the spectral resolution of the visible pulsar laser. That is around 0.6 wave number, while having the temporal and time resolution of the femtosecond laser of 35 femtosecond. I believe that these specifications, even up to now, still represent state of the art in the world. Okay, so I should thank Dr. Humphrey Wang for getting this system up and running and his continued support. Okay, in the next series of slides, I will show a few cases how our EMSL users have been using these some vibrational, some frequencies spectrometers in their research. In the case number 1 here, I show one research that published by Professor Franz Geiger's group at Northwestern University. In this research, they study how the pH and the aqueous phase concentration of ammonium sulfate and the concentration of beta-carotene aldehyde and the derivative that come from irradiation induced products there. And just because these, we know that beta-carotene aldehyde and the derivatives and also ammonium sulfate, these are really important chemicals for cloud nucleation. So hopefully through these studies, we have a better understand how the clouds are forming, if there is any possibility the human actually be able to mediate. Okay, on this slide, I just show some example spectra of this series of chemicals here. I just want to show that, basically for one, vibrational some frequency generation can definitely detect this series of molecules. On the left panel, I show the polarization combination of S and P, where S stands for the some frequency, the polarization of some frequency. The second S represents that of the visible, and the third that of the infrared. So for the SSB polarization combination, that we can see that these compounds, they actually varied quite a bit from either the relative intensity of the peaks on the number of peaks. And I just, for the future rest of the slides, I just want to point out that the peak around 2850, that is assigned to the stretch vibration, symmetric stretch vibration of CH2 group. And the one at 2880 is the symmetric stretch vibration of the CH3 group. And the 2920 is the asymmetric vibration of the CH2. So we just aware of this. I will not, continue to repeat. And also we see that through different polarization combination, we actually get different spectra. And in all the cases, the PPP combinations, the second column of the spectra, they are relatively invariant. So for all the rest of the presentation, I only show the SLP polarization combination. However, I should point out that PPP is very useful, particularly when we, I will not present today, but we can use this information to derive the orientation of molecules on the surface for specific systems. Okay, and on this slide, I just show that, for the chemical beta-carotene aldehyde, as the concentration of this chemical increased from 0 microgram to 100 microgram per liter, the VSFG SSP spectrum intensity keeps increasing. And at the same time, the ratio of the 2940, which is a fourth peak that actually assigned to the Fermi resonance of CH3. That to 2850 actually slightly increased. So that means that the structure of this molecule on the surface actually changing as its concentration increased. And they not just the change of the CH3 stretch frequencies, there is a lot of change also on the OH of the surface waters, where the 0 microgram was just a pure water surface. You can see that there is a strong peak around 3700 wave number. That is assigned, I have a circle there, assigned to the dangling OH group above the surface. However, once we have a beta-carotene aldehyde, this peak intensity drops significantly, which means that beta-carotene aldehyde actually come and absorb to the surface and takes away and suppress the OH that's been straddling above the surface. So that's why its intensity dropped. And at the same time, we also see that those OH stretch vibrations corresponding to so-called hydrogen-bounded regions. For example, the 3400 wave number region. Over there, for pure water, they have relatively broad and strong peak intensity there. However, once you have beta-carotene aldehyde, these hydrogen-bonded OH also got suppressed. And similarly, in the region of the so-called strongly hydrogen-bonded area in the 3200 wave number region. However, that is not as the reduction is not as severe as the weakly hydrogen-bonded area. So that means that this organic molecule, it really modifies the surface, not just the straggling water, but also the hydrogen-bound waters. On the next slides, I show one effect. Many people have heard this salting out effect. When we have an hydrophobic organic molecule on an aqueous solution surface, if there is no salt, on the salt concentration is low, you have a certain amount of organics that absorbed on the aqueous surface. However, if you increase the ionic strength, the salt concentration in the aqueous phase, people often observe this thing called salting out effect. It's basically before adding the salt, there could be a fraction of the organics actually dissolving in the solution. However, once you have salt inside in the solution, it actually pushes out the organics that originally dissolved in the aqueous phase. That's exactly what we observed here. On the left side, the bottom spectra, that's where there is no ammonium sulfate present. You can see that at 0 microgram, of course, there is no signal. However, if we increase the concentration of the salt to 20, without salt, if we increase the concentration of beta-carotene aldehyde to 20 microgram, they are dissolving in the solution, but we except a small dip around 2950 wave number, there is nothing of the organic groups to be observed. Only when we have the organic reaches 100 microgram, we see a strong peak of the organic CH3 and CH2 groups peaks there. However, if we have 1 molar ammonium sulfate in the solution, we see that while at 0 microgram, there's nothing there. However, even at 20 microgram per liter of the organic, we already see appreciable intensity. That means the salt pushes the beta-carotene aldehyde to the surface. So from here, we actually, from a molecular spectroscopy point, just specifically see such salting out effect occurred. And similarly, the same effect also saw on the OH stretch frequency side. Just look at those, the orange point over there, so that once we have the salt over there, originally intense hydrogen-bonded OH stretch peaks over there being suppressed, even at 20 microgram. So it's very similar, and that can just complement what observed in the CH group, CH stretch frequency groups there. Okay, that's the first example. The second example, I'm going to show, I will briefly go over these slides. Over here, we see how saccharide small molecules can actually affect the conformation and the orientation of lipid monolayers on aqueous surface. This also has potential atmospheric science background, but it also has strong applications or biological related research projects. Okay, so the lipid called DPPC, over here, I just show that that's a surface pressure and versus the molecular concentration plot. It's basically an adsorption isotherm here. For DPPC at different pHs and with glucosamine in the aqueous phase, we can see that there are two areas that we have different molecular structures for the DPPC. One is at 40 angstroms and one at 55 square angstrom. I should just point out that at 40 angstrom, that is corresponding to monolayer, a two-dimensional monolayer of DPPC. That the structure of the lipid is resemble that of the solid. And at 55, resemble of the liquid, condensed phase liquid. So we focus on these two regions. And then I show here that for this lipid monolayer, when it is two-dimensional solid, if there is no pH change, just pH adjust, no buffer, which just at the natural pH of glucosamic acid at pH power of 5.8, at different concentration from 0 to 10 millimolar, the isotherm is pretty much, featureless there. It's just not a whole lot of change there. However, we can see that once we apply phosphate buffers that go from 5.8, increased 8.5, 8.6, we can see that now that the distributions just increase quite a lot. So, which for one shows that we can, by changing the pH, and see different chemical behavior of the monolayers. And then if we look at under VSFG, we can see that at pH 5.8, without any buffer, the spectral signatures, just like the isotherm, is relatively with little change there. However, once we have buffer, that basically change the, all the DPPC and glucosamine, they all have a certain pKa value there. By changing their pH, we change the acid base. We basically doing acid base titration there. We're changing their acid base relative concentration. We see that by changing the relative acid base concentration of these species, we can affect the vibrational frequency of the lipid CH2 and CH3. And in this case, you can see that by increasing the concentration with both the peak at 2880, which corresponding to the CH3 symmetric stretching, and 2950, that's the Fermi band, they change quite significantly. So again, demonstrate that VSFG is sensitive and to be able to probe these chemical phenomena. And also similarly, for the 55 angstroms square DPPC, we can also see that now there is a lot of all the peaks are broadened, and particularly we can see that in the Fermi resonance region around 2950 wave number region, there are multiple bands appearing there, and they are changing as the concentration change, which means that when the lipid monolayers change from the two-dimensional solid form to the liquid condensed phase, they have way more different conformations. Basically means that those lipid, those alkyl groups can have different conformations and orientations there, and they change as the concentration increase. And I didn't show here, of course, they will change more significantly as the amide small molecules protonation status change and concentration change. Okay, let's give the second example. The third example and fourth example are all related to some of the processes, some of the projects that is on my home turf that's related to nuclear chemistry and nuclear processes. In this specific one, we tried, actually, this is a project we collaborate with a group at Washington State University, Dr. Sue Clark's group, and this is actually part of one of the graduate students' PhD dissertation work. Okay. And we know that many people, particularly in the nuclear chemistry, with nuclear chemistry background, there is this process called Purex. It's basically for all the irradiated nuclear rod, that's for all the weapons production and the power generation that you, through a neutron bombarding, convert a portion of the uranium into plutonium. And the reacting uranium plutonium need to be separate from the rest of the transition metals and the lanthanides. The technique here is called Purex. Basically, use tributyl phosphate to contact with acidic solutions of dissolved nuclear rod. And in this process, the TBP molecules can complex with uranium and plutonium nitrate and form a neutral adducts that extract these two ions into the organic phase and leaving the rest of the transition metals and lanthanides in the aqueous phase and separate these two important elements from the rest. However, the detailed chemical processes are only really poorly understood. That's why we try to see if we can actually see such chemical processes. To aid the study here, instead of TBP, we use a DBP. The DBP has a more appreciable solubility. There is some more other information makes the study easier. Okay. I just want to show in this slide that indeed, the VSFG technique really has some really, interesting properties that to be observed. Like in this case, on the left panel, I show a typical VSFG spectra for water. You can see that there is one sharp peak around 3700 that, as I mentioned, is corresponding to the diagonal edge. And then there is broad peaks from 3000 wave number to 3600 wave number that basically spans all of those hydrogen bonded, symmetric and asymmetric stretch frequencies of OH. However, once we have just 0.24 millimolar of DBP molecule, interesting observation happened here. You can see that for one, if you look at the 3700 wave number, and we can see that just the addition of 0.24 millimolar of DBP, it is suppressed the diagonal LH bond to by like almost 40%. Very interesting observation here is that, typically we would have imagined that by adding this organic molecule, you possibly just take away the water molecules on the surface and, reduce the intensity of the hydrogen-bonded OH spectra. But in the contrary, on this spectrum, what we see that once added 0.24 millimolar of DBP, we not only see the CH band appearing at 2850 and 2950, we also see that the hydrogen-bonded OH peak intensity increased like 3 times. That's really interesting. What happened is that because we have those, dibutyl phosphate groups here, and possibly at such a low concentration, majority of the HDPP actually deprotonate, formed anion. So we have an electrified interface there. Because of that, it realigned more water molecules there, and because of that, we actually see a significantly enhanced aqueous spectra. This is really interesting because this can have serious consequences for a lot of biological systems and the environmental system that involves organics and biological molecules, microbes, so that it will significantly change the interfacial hydration structures that of significant implications. So many people may find such information to be useful to gain chemical insight for different chemical systems. And I think the rest of a couple of slides, I'm not going to spend too much time. Basically, as DBP concentration increase, we definitely see that the CH groups increase, as shown in the top left panel and plot in the lower left panel. And we also, through surface tension studies, we see that by increasing the organics, we didn't reduce the surface tension. That's why we got more. Okay. That indicates that we get more organic molecules on the surface. And very interestingly, we see that once we change the acidity, in this case, we increase the nitric acid concentration from 0 to 0.008 molar, 0.08 molar, and 0.1 molar. We can see that by increase the concentration of nitric acid, we significantly increase that the CH2 and CH3 peak. However, we drop the OH stretch frequency intensity. That is because by acidifying the solution, we protonate the surface DBP molecules and reduce the electric properties there, charge there. That's why we got the reduction of intensity here. So that's again show the possible potential application of this technique. Okay, in the last example, I show something that is nature on a solid surface. In this case, we try to differentiate the OH groups on gibbsite surface as versus to the bulk. Okay, and the background of this is in the tank waste. We always thought there is radioactive material there. It turns out the majority, about 70% of the sludge actually composed of aluminum mineral phases, such as gibbsite and bomite. And in the current process, we need to separate these phases out. So studies of this will aid the transport of these phases into the vitrification plant. Okay. What happened is that from the initial tries, folks in the tank waste reprocessing have found that the pipes get clogged very easily. And of course, because the majority are alumina phases, the immediate suspicion would be that the alumina phases somehow they got nucleated and agglomerated. That's into big chunks of solid that how they plug the pipes. So something happened on the surface of these particles And most, either from surface passivation by irradiation, absorption of metal ions, incorporation of metal ions, and so on. So we are basically studying all of these processes. I just show one example in the next few slides. Over here, I show that for gibbsite, for one, it has really beautiful vibrational signatures. In gibbsite, it has 6 different kind of OH groups, 3 of them at the interlayer, 3 of them at the interlayer, and each has distinct vibrational stretch frequencies. However, 2 pair of those frequencies, they are so close. So in a typical study, we only see just like 4 peaks. That's exactly what we see here. I'm going to skip these few slides, basically show their X-ray diffraction and so on. And I want to point out that for gibbsite, this is a SEM picture and atomic force microscope. Before and after gamma ray, which from cobalt-60 irradiation, their morphology basically look exact the same. And also the same thing, if you record the infrared spectra of both gibbsite boehmite, the signatures look very similar, except for boehmite, where the Raman spectra shows some overall reduction of the peak in intensity in the OH stretch region. However, once we look at vibrational some frequency generation, we see big changes here. On the left 2 panels, on the left, the very left panel, I show the the Raman spectra of gibbsite before and after gamma irradiation. We can see that the peak intensities, there is a small amount of reduction of peak intensity at 4 bands observed there that corresponds to the OH stretch frequency. It's about like a 30% reduction, 30 or 40% reduction there. However, once we subject the gibbsite to gamma irradiation, we can see that the intensity dropped significantly. It's basically only like 85, 90% of OH groups are left over there. So what it shows there is that gamma irradiation preferentially dehydrogenate the surface hydroxyls. So then the surface oxygen radicals possibly somehow interact and modify the surface structure. So that potentially contribute to the change of the surface properties, which might contribute to the aggregation behavior there. And it was really interesting that once you subject this material to irradiation, and if you re-irradiate and come to ambient conditions, the reactions won't be reversed anymore. It's a permanent damage. Okay, so it's the same thing observed for boehmite. I'm not going to say more about that. And also, I just want to say that, in EMSL, we have a suite of other techniques also. For example, here I show the EPR spectra of the irradiate gibbsite. We can see that for both boehmite and gibbsite, after irradiation, we see different kind of reaction intermediate, those radicals. And some of the radicals that can survive a long time after the irradiation. Okay, I think that's all about some frequency. I just want to spend 1 minute because before the the seminar presentation, many people ask me, are there any other techniques can be specifically useful to critical minerals, critical element studies? I just want to mention that in our lab, in the environmental spectroscopy lab, we also have so-called laser-induced time-resolved luminescence spectroscopy capabilities. Many of the trivalent lasonides display beautiful absorption and fluorescence spectra with long fluorescence lifetimes. And these, their spectra, their lifetimes are variant changes a lot as their coordination environment change. I show spectra changes here. And particularly for this, the luminescence lifetime shows a lot about their coordination and particular hydration. Through these changes, we can specifically monitor how these chemical species change. For example, this is the specific spectrometer we have. We can change from room temperature to liquid helium temperature. And I just show one example here. We were able to use this technique to see how the trivalent europium being uptaken by plant root. We can do this actually in situ, in vivo. And we can discriminate the strong fluorescence from the root, like a tryptophan and other root fluorescence species, and selectively see the europium that binds to root and transported from the root to the leaves. And we can, by doing a cross section, we can also see at different the root elements how the europium are being distributed. This can have a lot of usefulness, both for like a photo remediation, photo extraction of critical elements, and other studies. Okay, I think that's all the cases I wanted to show. And we have many collaborators, EMSL users has contributed to this work. And I'm not going to go through in any detail. And of course, as a conclusion, instead of give specific conclusions, I just want to point out, you see that, the VSFG can be used to probe all the stretch and bending vibrations, just like Raman and infrared, but specific for the interfacial molecules. Wherever there are interfacial reactions, we may be able to contribute pneumatics, power system, environmental system, energy system, battery studies, and so on. Okay. And I would like to thank the supporter of BER and EMSL, and we all know that EMSL is a BER user facility, and welcome to contact us for future collaborations. Thank you.
All right. Thank you, Zheming. That was very informative. And our attendees thought so also, because we have quite a few questions for you. Beth, if we can stop the screen. All right, thank you. Okay, so Zheming, the first question from the audience. Are there fields of research that aren't currently using FSG that you would be excited to see this method applied to?
Oh yeah, absolutely. For example, I write at the moment, we have one user project from renewable energy, and it's Spectroscopy groups. They are trying to see for some of the protein molecules how the surface behavior under different conditions. That's a biological related system, and we can contribute definitely. That's why going on. However, for as I show for the atmospheric science, but for critical elements, we know that like lithium and rare earths, a lot of them actually exist in the ionic form and being absorbed in like clays and phyllosilicates. So the interfacial and interlayer molecular speciation information will be important to designing ways to extract these elements. I hope that users will make use of this technique along with the time-resolved luminescence technique. We can detect how these adsorption occur, what kind of chemical bonding, and help our research. For sure. And the other area will be like batteries and electrolysis. The reactions are occurring specifically at the electrode surface. And, same thing for catalysis where, gas molecules and aqueous phase molecules at the solid interface. So we hope to be able to design systems that we can actually study these systems in operando, so that while the reactions being, the system being biased, and we see exactly what's going on. So these are some of the examples, but I'm sure many systems will be really interested.
Yeah. Okay, next question. Could you please share what the current time resolution of FSG system is? So what is the current time resolution?
Okay, the current particular, I think is actually from what my interaction in the field, the time resolution is still on the tens of femtosecond time resolution. So our broadband system is about the best of the, in the field.
Okay.
Yeah, you actually raised a good. This is really raised a good question. In the nonlinear spectroscopy field in the SFG research area, some people they do like a pump probe type of dynamic studies, and which we don't have, but it's something that without too much difficulty we may add, so that will particularly be useful, and in that case the time resolution will be very much useful for some of the picosecond dynamics, such as hydrogen bonding and so on, which on the order of a picosecond, 2 picosecond region. So tens of femtosecond time resolution will allow these studies to be executed.
Great. With the electrified interfaces, do you account for higher order, like a Chi3 effect? And would this have an impact on the resulting conclusions?
Oh yeah, for sure. That, particular, I would say, we haven't performed much of these type of studies. It's something and we have intention, but we currently don't have projects to really work on. But Franz Geiger's group at Northwestern, they are really pioneers, are really advanced in this area. I would, encourage readers to read Franz's publications, particularly in this area. And I would point out that, on the research team here at in our group, Mavis Bowman, who is a former PhD student from Franz group, she is actually really good at this as well. So it's something we can actually possibly, learn and implement pretty quickly.
All right. You mentioned that your pico system or your picosecond system is your workhorse. Is there a reason that system is favored over the broadband one?
No. Okay. For one, it's just, the broadband system, it involves synchronization of a picosecond, a femtosecond laser. So it is instrumentationally, it's way more involved. Okay, it does provide the broadband, which are much faster detection. And for the same quality spectra, you can get in 2-3 minutes, possibly takes 20-30 minutes or more on the scanning system. But for that system to operate without interruption, it takes a lot of effort. Okay, and plus the lasers are, 15 years old, and these lasers that produced that long ago tends to be not as stable as other systems. So that's why the scanning system it's more reliable. Take less attention, and the other one really needs a lot of attention. So need more support.
All right.
Yeah.
What recent advances in FSG and SHG methodology are you most excited about, and would you like to see developed at PNNL? And then also, why do they excite you?
Okay. there are several fronts over there we would like to have, and we actually looked into them, but at the moment just don't have the manpower and the resources to pursue. I would say there are at least 3 areas. One is to go with VSFG macroscopy. So instead of like right now, it's a bulk analysis, we possibly monitoring at least 200, 300 micrometer area. We hope to be able to integrate with a microscope system that we can have high spatial resolution down to a few microns at least. That will be really useful for a lot of applications. Second, as I just indicated, will be that we hope to be able to integrate the pump probe capabilities so that we can study the dynamics. And the third, this has been reasonably mature in the field, and particularly, pioneered in Michel Brown's group in Max Planck Institute. Not, the current system, we use a specular reflection geometry to study interfaces. So typically require a more or less flat bulk surface there. However, there are techniques has been developed to study this phenomenon in scattering mode. So scattering some frequency studies. In that case, we can look at suspensions, for example, on porous solid, on that solid molecules that is being incorporated into a transparent media. So that has way more into chemical systems and way more relevant systems for many practical research. So these 3 are some of the systems that we would like to get into.
All right. Okay, last question that we have in the queue right now. With respect to the previous time resolution question, does your system use I'm sorry, my tongue just got tied. Does your system use an etalon for pulse shaping to achieve the femtosecond time resolution? I'm sorry, I hope I pronounced that correctly. Etalon?
Yeah, actually.
Okay. So does your system use an etalon for pulse shaping to achieve the femtosecond time resolution?
I don't think so. I think if there is, that would be in the fundamental frequency of 800 alpha laser, but there could be, I just, for the moment, I just got rusty over there.
Did we stump you?
No. We do have the pulse compression there. I think the principle is like etalon. At least principle is like etalon. Yeah, I have to double check on that one.
All right. Well,
yeah.
Unfortunately, the person who put that question in the Q&A is anonymous. So we won't be able to, or you won't be able to respond back to them. But in the chat, you will see, for audience members, you will see that we put Zheming's email address. If you have any other questions for Zheming, please go ahead and email him. Yeah, if you have any further questions. Because with that, thank you for joining us. Today's webinar is over, and we hope to see everyone on June 11th for our next webinar on critical minerals, interrogations on their behavior. So thank you so much.
Thank you.